Okay, today we are going to discuss amino acids. Uh, this is for today's session, and we are particularly discussing the structure of amino acids. What are amino acids? By the name itself, we understand they consist of two functional groups: carboxylic acid and amino functional group. And because of these two functional groups or difunctional nature of amino acid, they are present in ionic form. So let's discuss what we mean by ionic structure of amino acid. As we know, amino acids are difunctional, that is, they contain both an acidic group and a basic amino group like carboxylic COOH and NH2. In dry state, these amino acids exist as inner salt. This inner salt is formed when the proton of carboxylic acid is transferred to amino group. Okay, this is because of the intramolecular acid-base reaction. The acidic proton of carboxylic acid is transferred to basic amino group, and because of that, the structure we get is of a dipolar ion nature, which is known as Zwitter ion form of amino acid. The dipolar ionic structure of amino acid is represented like this. In this structure, you can see the acidic proton of this carboxylic acid is transferred to the amino group. Okay? And in the same molecule of amino acid, we have a cation, positively charged amino group, and an anion, negatively charged carboxylic acid group. And this dipolar ion, cation and anion present in the same molecule, this form is known as Zwitter ion form of amino acid. Next, we are going to discuss what is isoelectric point. It is represented by Pi. When we write a dipolar ion form of amino acid, we called it as Zwitter ion. It exists in equilibrium with the cationic form and anionic form in the aqueous solution. If we dissolve an amino acid in water, we get the aqueous solution form of that amino acid. And as we have discussed, the Zwitter ion form, which is a dipolar form. In the aqueous solution, that Zwitter ion form is in equilibrium with the cationic form and anionic form of an amino acid. Now, out of these cationic anionic form, the predominant form is depends on the pH of the solution. When we say a particular form, say cationic form of amino acid is in major proportion in the aqueous solution, so it depends on the pH of the solution. So pH of solution plays an important role, okay, for the population or the majority of ionic form of an amino acid. Now, when we have a strong acidic solution, then the amino acids are present primarily as cations, whereas in strongly basic solution, they are present as anions. It can be shown with a reaction represented here. This is the dipolar ion form or Zwitter ion form of an amino acid. Okay, in acidic or basic solution, okay, we have a cationic form which is dominant in acidic solution, whereas in the basic solution anionic form is dominant. Now, when we put this amino acid, okay, a solution, okay, then it is found that depends on the pH, it migrates towards cathode or anode. So, when I say if the solution is acidic in nature, then amino acid will migrate towards the cathode in the solution. Whereas, if the aqueous solution is basic in nature, then the amino acid will migrate towards the anode. So now we are going to define isoelectric point. It is defined as the value of pH at which the amino acid does not migrate to either cathode or anode under the influence of electric field. It's called as isoelectric point of the given amino acid. The value of pH at which the amino acid does not migrate to either cathode or anode under the influence of electric field is called its isoelectric point. Every amino acid has characteristic isoelectric point. The pi values for few amino acids are represented here. For amino acid, example glycine, it is 5.97. For alanine, it is 6.01. And for aspartic acid, it is 2.77. So let's discuss synthetic methods for amino acids. First of that is Strecker synthesis. In this method, we require three reactants: an aldehyde, hydrogen cyanide, and ammonia. When these three reacts, the first step gives alpha amino nitride, which on acid hydrolysis gives the corresponding alpha amino acid. The reaction is represented like this: aldehyde, ammonia, and hydrogen cyanide first gives alpha amino nitride, which on acid hydrolysis gives amino acid. This Stecker synthesis is very useful method for the synthesis of amino acids like glycine, alanine, serine, valine, etc. Here, depending upon this R in the aldehyde, we can design the synthesis of different amino acids. If the reaction is started with acetaldehyde, where R is equal to CH3, okay, the amino acid form will be alanine. Okay. If we start when R is equal to an isopropyl group, then this Strecker synthesis will give valine as an amino acid. So remember, as the nature of R in the aldehyde changes, we can design the synthesis of amino acids. The next method of synthesis of amino acid is known as Gabriel's thalamide synthesis. In this method, the amination of alpha haloester is carried out with potassium salt of thalamide. The reaction is carried out in two steps. The step 1, the potassium salt of thalamide reacts with alpha haloester. With the loss of potassium bromide, it gives me an adduct. In the step 2, this adduct will be hydrolyzed using sodium hydroxide. Okay. This results in the cleavage of this amide bond and hydrolysis of this ester also, which on the acidification gives the corresponding amino acid and phthalic acid as the byproduct.